So we have talked about, well, what are we on? We're on macroscopic deformations. And statically indeterminate structures. And so we started out with tension and compression. We figured out how to calculate the elongation, and then we used that for statically indeterminate systems. And then we did it for torque, internal torque. Figured out how to calculate the angle of twist, and then we use that in statically indeterminate systems. So we're done with those. And the last one that we have to do is for bending moments. You know, you might think we also need to do it for shear force, but remember that shear force and bending moment are related through that derivative relationship. And so we only have this one left to do. So this is the deflection due to bending moment. And for this, we're going to use the theory of elastic beams. That says you're assuming that the length of the beam is much larger than the thickness. Then if you take the bending moment at a point and divide it by the Young's modulus times the area moment of inertia, this thing together here is called the flexural rigidity. Then that has to be equal to the curvature of the beam at that point. You guys remember talking about curvature in Calc something? Calc 3? Yes, that's right. And so the curvature use the Greek letter kappa to represent that. Let's say of a function parametrized by arc length is the derivative of, what do we call this function? So I'll call this one g. So of a function G of S, S is the arc length, is dg ds. For us, though, we're going to be dealing with functions of the horizontal position x. So the curvature of a function f of x is this really ugly expression. It's equal to the absolute value of f prime, f double prime, sorry, absolute value divided by the quantity 1 plus the absolute value of f prime squared, all to the 3/2 power. Okay, well, it'd be nice if we were doing it in terms of arc length, obviously, but we're not. So that's this messy thing. But the good news is, okay, so this is a mess, but notice what happens if f prime of x stays close to 0. If f prime of x is close to 0, you can approximate the curvature by the relationship kappa is equal to the second derivative of x. So, I mean, just look at this this function, what happens. This is close to, if this is reasonably close to 0, then you square it and it gets closer to 0. Like say this is equal to 1/10 or something. You square 1/10, you get 1/100th. And so this, the denominator, gets really close to 1. And then you just have the second derivative on top divided by 1. No, so I guess that is the, that's the, I guess you could think of this as the absolute value of the curvature. And then you need to think about whether it's concave up or concave down to come up with the sign. But we're just going to use this function here. Yay. So why does this work? Like, let's be clear about that. I think this sort of helps understand what this function is that we're talking about, sort of. Why can we assume f prime of x is close to 0? That is true. Our function f of x is the displacement of the beam from its reference location at any value x. Okay, so if we start out with a beam like this, let's say On the left end, we have a pin joint, and then our reference position of the beam is like this. Okay, and let's say we have a roller somewhere too, like this. And now the beam is deformed. This is exaggerated, but let's say that the beam does that. Okay, so then this distance here, yes, that distance there is our value f of x for that x value. Okay, and so if we're starting out with a beam that's horizontal, like we're always doing with these beam problems, what does that f prime of x represent? So it just represents the slope of that thing, of that beam in its deformed state. So f prime of x is the slope of the beam, location x. And since we're assuming small deformations throughout this whole class, the slope stays close to 0. And if the slope of that beam stays reasonably close to 0, then you square that for the curvature formula, and you get something that's even, that denominator is even closer to 1. Yes? Well, we can assume that, no, not necessarily. But it does sort of depend on where, like, I guess it is just sort of like a matter of like degree or something. I think probably the easiest way to make sense out of that is just because of this square, this could be reasonably close to 0, but this is close to 0 squared, Also, you can have, for most of this class, we've been assuming that deformations are small, like small enough that the strains are pretty small, But if you have a single beam, well, let's think about this sheet of paper, Right now, every point on this piece of paper has a small strain, but the slope of this paper is not small, and we wouldn't be able to make this assumption. So we're sort of taking the fact that we're dealing with, in a sense, what we're saying here isn't like a mathematical assumption. It's an assumption based on like the engineering materials and shapes of engineering beams that we're going to be using. You just know, like, if you're using I-beams or something, a big steel cantilever post coming out of a wall, that slope it's not going to dip down very much. It's not really mathematical certainty, but we're going to make that assumption. And we're glad we can make that assumption because it simplifies the math. Okay. So we know that that function x, that function f of x is the deflection, and I guess we're going to use lowercase v to indicate deflection. Okay, so what do we know? Then the elastic beams equation says the deflection double prime is equal to the bending moment divided by EI. And this has to hold every x value. Okay, so that's a second order differential equation. Second order ordinary differential equation that we can solve by separation of variables. Let me write that out. Separation of variables. Or it's simple enough that you can just think about it as integrating twice. So if you integrate v double prime dx, that has to be equal to the integral of m, I guess we can pull the constants out, divided by EI dx. And so that says that v prime is equal to 1 over EI times the integral of m dx. And then integrate again, and v is equal to 1 over EI times the second integral of m. Sort of it's a simple thing to do. When we put numbers to it, it'll be simple. Here it looks sort of messy. But what happens when you take two integrals of something? This is going to have two constants of integration. And to solve for those two constants of integration, we're going to use the boundary conditions. And those boundary conditions are going to, the boundary conditions that we're going to know are going to be at the joints. So we're going to be dealing with two types of joints. The first one is fixed joints. And so at an x value, where the beam has a fixed joint, a deflection at that x has to be equal to 0. That's saying that if you, well, I don't have a picture of a fixed joint here, I have a pin, but it works this, for the deflection, it works the same as at the pin. This beam being attached to that pin says that right at that location, that beam can't move at all. You know, if you move away from the pin, these all have non-zero deflections, but at the pin, that deflection is fixed. Okay, so that's how at a fixed joint we know that V is equal to 0. But at a fixed joint, we know something else too. At this pin and this roller, we don't know anything about the slope. And you can see that pretty clearly the way that I have it drawn here. You know, here the slope is positive at this pin joint. Here the slope is negative. But if you have a fixed joint, not only is the deflection set to 0, but the slope is also set to 0 at that location. So V prime also has to be equal to 0. Okay, so let me draw that. So let's say that we have a cantilever beam, and that initially the beam has this shape. Okay. Then under deformation, the location of this beam and its slope have to stay that way. Then after that, it can do whatever, you know. Yeah, that's very exaggerated, and we wouldn't be able to assume that V prime is equal to 0 there. But right at the wall, we have V equals 0, and V prime is equal to 0. It's true. That would be hard. That's what it does. I learned that the hard way. Okay, and then the other type of joints that we're going to deal with are pins and rollers. You treat both of those the same. At those, we just know that the deflection is equal to 0. We don't know anything about the slope. So, like in the example that I drew at the start, if you have a pin and a roller, and originally the beam has a shape like that, then after the deformation, it could do something like that. Here and here, the deflection is equal to 0, but the slope is whatever. Okay, there's one more thing that we're going to have to deal with, and that is you know, sometimes the bending moment is represented as a piecewise function. We saw that all the time in internal loads calculations. Is a piecewise function. So, you know, m of x for example, could be equal to negative 500x for x between 0 and 2, and then 500x minus 800 for x between 2 and 3 or something. That was something that came up pretty often with internal loads. In that case, at the, call it the seam, where the piecewise function changes, the subfunctions change. Two things have to happen. First, the deflection using the subfunction from the left has to equal the subfunction coming from the right. That means that the beam, there's no discontinuities in the beam. And also, the first derivatives of the two subfunctions have to be equal at the seam. So v prime at the left has to equal v prime at the right. And that says that the beam is smooth at that seam. Anybody have any questions yet?
Is there any bending that can happen to an IV that increases its strength?
Increases what?
Its strength or its bending?
No elastic deformations. I don't know what happens once you get into the plastic range. I think there is some stuff like that. But for what we're interested in this class, no. Okay, let me do an example. So let's say we have a cantilever beam, and it has a uniform distributed load. With a value of 10,000 newtons per meter. The length is 3 meters. And we want to calculate the deflection as a function of x. Let's say that modulus is 200 times 10 to the 9 steel. And the shape of the cross-section is such that the area moment of inertia is 8.3 repeating times 10 to the minus 7. And that's meters to the fourth. And let's calculate this, and then let's use it to figure out what's the total deflection at the right end. Well, what do we need? All of this depends on knowing the internal bending moment as a function of x. So we have to calculate the external loads at the fixed joint, and then calculate the bending moment as a function of x, and then work from there. Then we start doing the integration and stuff. So first free body diagram of the whole beam. The total force, we'll just treat it as a point force for this, is 10,000 times 3. And then at the end, we have an unknown force vector and an unknown reaction couple, call that MR. So Newton's second law says Rx, Ry, plus 0, negative 3,000, 30,000, is equal to zeros. So this force vector R is equal to 0, positive 30,000. And then the moment equation, I'll calculate the moments around the left endpoint. So there's nothing, no moment produced by R. There is MR. And then what's the moment arm for the 30,000 Newton force? Yep, 1.5 times 30,000. And then is it positive or negative? Negative. That's equal to 0. That reaction couple is equal to positive 45,000. The force is newtons. This is Newton meters. Okay, so now we have the external loads. Now we can calculate the internal loads. And all we're doing this for is to get the bending moment function. Look back at this original picture. How many cuts do we have to make? 1. And so cut 1 is valid for all the x's, 0 to 3. So over here we have an upward force of 30,000 and a positive couple of 45,000. And then we have a distributed load. The length of our cut is x. The distributed load is 10,000. So if we treat that as a point force, this is 10,000 x. And our internal loads, T, V, M. So Newton's second law says T negative V plus 0, positive 30,000 plus 0, negative 10,000 x is equal to zeros. So T is equal to 0. V is equal to negative 10,000 x plus 30,000. Now we'll go to the moment equation. Our about point is at the left end point again. So we have the couple of positive 45,000. We have the 10,000 x force with a moment arm of x over 2. So x over 2 times 10,000 x. And is that clockwise or counterclockwise? Clockwise, so negative. And then plus m minus vx is equal to 0. So M is equal to negative 45,000 plus 5,000 x squared plus Vx, which is minus 10,000 x squared plus 30,000 x. So M as a function of x is equal to, I guess I'll rearrange it as negative 5,000 x squared plus 30,000 x minus 45,000. And you can check and make sure that dm dx is equal to v, and it is in this case. Okay, so now we know that, so now we're going to calculate the deflection. And we know that V double prime is equal to 1 over EI. I'll just leave it as a variable for now. Times this function, the quantity negative 5,000 x squared plus 30,000 x minus 45,000. Rate that once, and you get V prime is equal to 1 over EI times the quantity negative 5,000 divided by 3 is negative 1666.6 repeating cubed plus 15,000 x squared minus 45,000 x, and then plus some constant that we'll call C1. That's the constant of integration. And integrate again, and you get that V, the deflection as a function of x, is 1 over EI times the quantity, what's that divided by 4? Okay, so negative 416.6 repeating x to the fourth plus 5,000 x cubed minus 20, what? Yep, x squared plus C1x plus C2. So now we have both of those two constants of integration, and this is the deflection as a function of x. And this is a true statement, but we just don't know what C1 and C2 are yet. You know, you can't debate this, but we'd like to know what those values are. All right, so now we want to use the boundary conditions. Use the boundary conditions to find C1 and C2. Well, what we know is, look back at the original picture, we have a fixed joint at x equals 0. So we know that the deflection at 0 has to be equal to 0. And v prime at x equals 0 has to be 0. Well, let's use the v prime first. So we have this expression right here for v prime. That says that 1 over EI times the quantity, we have 0 plus 0 plus 0, because because we're plugging in x equals 0 to all these, so any polynomial terms are 0. And then we have plus 0 plus C2. Oh, yeah. Plus C1. And this is equal to 0. Yeah, right. Okay, so we know that C1 is equal to 0. And so now we can update what we know about our deflection function. So V of x is equal to 1 over EI times the quantity, negative 416.6 repeating, times x to the fourth, plus 5,000 x cubed, minus 22,500 times x squared, plus 0 plus C2. And now we'll use this deflection function and what we know about the deflection at x equals 0. So plug x equals 0 in for this function, and you get 1 over EI times 0 plus 0 plus 0 plus C2 is equal to 0. So C2 has to be equal to 0. And so our final deflection function is 1 over EI times negative 416.6 repeating x to the fourth plus 5,000 x cubed minus 22,500 x squared. And now we can plug in 1 over EI. Can someone multiply, get that flexural rigidity? Just multiply those two numbers together. I guess 16.6 repeating times 10 to the 2, 1.6 repeating, I guess 1.6 repeating times 10 to the third.
Thousands, there are 166,000 times here. First one is negative 6.9.
Alright, so you got negative 2.5, that's 10 to the negative 3 x 4, or x to the 4th.
For that first term or for the, okay, negative 2.5.
Oh, did you want why to have that?
Okay, 6 times 10 to the minus 6. And then all these are just the, okay. So negative 416.6 repeating x to the 4th plus 5,000 x cubed minus 22,500 x squared. I'll just leave it like that, that's fine. Okay, so this is our final expression for the deflection. So that's the answer for part A. Then we also want to plug in x equals 3 and see what the total deflection is over the length of this beam. Could a couple people punch in those values and make sure the answers agree? So the deflection at x equals 3. Okay, well, that's a pretty big deflection. So that's probably not realistic for the approach we're taking. If you think about this beam being only 3 meters long, and the deflection would be something like this, you know, where this length is 3 meters. And so you can see from looking at it that we'd have to have points where the slope of that beam is pretty big. And so our assumptions wouldn't hold very well. So this isn't a great example of like a practical situation where you would trust these results. But that's the approach you would take. In a more realistic problem, or in a, it's not that this problem isn't realistic, it's just that the method we used wouldn't work in this case. But if, what did I have initially? The distributed load was like 10,000 newtons per meter. If it was something more like 1 or 2,000, we'd get a much smaller deflection. That slope would stay close to 0 the whole time, and the results that we got would be trustworthy, Any questions about that? All right, so next time, really the last thing we have to do with statically indeterminate systems is figure out, next, we'll use this for statically indeterminate systems like for example, what if you had a cantilever on the left and then another support somewhere like this? And then you add, your loads. Well, you can't do this as a statics problem because you only get 3 equations for this, and we have 3 variables for the load here and another variable there. So 3 equations, 4 variables. We couldn't solve that. But now we'll be able to get an additional set of equations that say there can't be any deflection or slope here, and there can't be any deflection here, and that'll give us the extra stuff that we need to figure out, to be able to solve for those external loads. Then we could go back and calculate the internal loads, calculate the deflection. Any questions? Ooh, I went over. Okay, see you Wednesday.